Welcome. Today, we're diving into the essentials of chiller performance, how to understand it, calculate it, and make it run more efficiently. This guide is designed for new engineers, a complete beginner's roadmap to mastering chiller efficiency. Let's get started and build a solid foundation together. Chiller systems are the biggest electrical consumers in most commercial and industrial buildings. They can use anywhere from 40 to 60% of a building's total electrical power. That's huge. A chiller works by pulling heat out of water and releasing it outside through a condenser. The cooled water then circulates through air handlers or other cooling equipment. Because chillers use so much energy, keeping a close eye on their efficiency is key. It helps cut costs and keeps everything running smoothly. Let's talk about efficiency, specifically, why every HVAC engineer needs to know how to calculate chiller efficiency accurately. When efficiency drops, problems pile up. Maintenance costs go up, equipment wears out faster, and compressors work harder than they should. Cooling capacity drops, electricity bills climb, and overall power consumption rises. Understanding this impact is crucial, because low efficiency doesn't just waste energy, it strains the whole system. This sets the stage for everything we'll explore next. This document is designed to guide new engineers through key concepts in a clear, straightforward way. We'll cover practical site examples and common mistakes to watch out for. You'll learn important operating parameters, how variable frequency drives affect performance, and why efficiency changes under different loads. We'll also explain refrigeration calculations, how to work with both metric and imperial units, and break down what COP means, and why it matters for chiller efficiency. This introduction sets the stage for everything that follows. Let's talk about chiller efficiency, what it really means and why it matters. Simply put, a chiller is more efficient when it uses less electrical energy but delivers more cooling power. So, chiller efficiency measures how well a chiller turns electricity into cooling effect. It's a key way to understand performance. The higher the efficiency, the smarter the energy use. This concept sets the stage for everything we'll explore next. Let's start by looking at the main parts of a chiller: the expansion valve, condenser, compressor, and evaporator. These components work together in a cycle, with the refrigerant constantly flowing through them. Most of the electrical energy powers the compressor motor, which drives the whole process. Before diving into efficiency calculations, it's crucial to grasp how these pieces interact and how the cooling process actually happens. This foundation makes everything that follows much clearer. Let's walk through the refrigeration cycle step by step. It starts in the evaporator, where warm water from the building passes through, and the refrigerant absorbs heat, cooling the water. Next, the compressor kicks in, raising the refrigerant's pressure and temperature using electrical energy. Then, in the condenser, heat is rejected to the atmosphere, often with help from cooling tower water or air. Finally, the expansion valve lowers the refrigerant's pressure, cooling it down again, ready to repeat the cycle. Let's talk about COP. That stands for coefficient of performance. It's a way to measure how efficient a chiller is. Simply put, it's the ratio between the cooling capacity it provides and the electrical power it consumes. So, if a chiller uses less electricity to produce more cooling, it has a higher COP. This number helps us understand how well the system is working, and it's key when comparing different chillers or optimizing energy use. Let's break down what COP really means, in simple terms. COP stands for coefficient of performance. It's a measure of efficiency. A higher COP means better efficiency, lower energy use, and a smaller electricity bill. For example, if a chiller uses 300 kilowatts of electricity to produce 1,800 kilowatts of cooling, its COP is 6. That's 6 times the cooling for every unit of energy consumed. Lower COP means the opposite: more energy, more cost, and potential maintenance headaches. When we look at chiller performance, several factors come into play: maintenance condition, ambient temperature, chilled water temperature, condenser water temperature, and load condition. These all affect how efficiently a chiller runs. Different types of chillers have typical ranges for their coefficient of performance, or COP. Older reciprocating chillers might range from 2.5 to 4, while high-efficiency magnetic bearing chillers can reach between 7 and 11. This comparison helps us understand where efficiency gains are possible. Let's talk about how we measure chiller efficiency using the metric method. It's pretty straightforward. We take the cooling output in kilowatts and divide it by the power input, also in kilowatts. Since both cooling and power consumption are in the same units, the calculation becomes simple and clear. This ratio, called COP, helps us quickly understand how efficiently a chiller is working. It's a practical way to compare performance across different systems. Let's take a closer look at what good efficiency means for a centrifugal chiller. Here, the coefficient of performance, or COP, is 6. That means for every 1 kilowatt of electricity we put in, the chiller produces 6 kilowatts of cooling. We calculate this by dividing the cooling capacity, 2100 kilowatts, by the electrical power input, which is 350 kilowatts. A COP of 6 is considered quite efficient for this type of system in a commercial building. Before we can calculate the coefficient of performance, or COP, we need to get our cooling capacity into the right units. That means converting whatever measurement we have, whether it's tons of refrigeration or BTUs per hour, into kilowatts. Different countries use different standards, so this step helps us speak the same language when we talk about chiller efficiency. It's a crucial first move in understanding how well our system is working. Let's start with a key conversion you'll see often. 1 kilowatt equals 3,412 BTUs per hour. This is the standard way to switch between these units of power and heat. Understanding this lets us move smoothly between different measurement systems, especially when dealing with energy or heating calculations. It's a simple but essential step in making sure we're all speaking the same language when it comes to power. Let's walk through how we calculate the coefficient of performance, or COP, using imperial units. First, we convert the cooling capacity from BTUs per hour into kilowatts. In this example, 6,824,000 BTU per hour becomes 2,000 kilowatts. Then, we divide that cooling capacity by the power consumption, which is 400 kilowatts. The result is a COP of 5, a straightforward way to measure efficiency in this system. Let's talk about what affects cooling capacity. It really boils down to two things: the temperature difference and the water flow rate. The chiller works by pulling heat out of the chilled water, using refrigerant to do the heavy lifting. The amount of heat it removes is what we call the refrigeration effect. In simple terms, it's the measure of how much heat the chiller can take away from the water. That's the heart of refrigeration. Let's break down the key formula behind cooling capacity. It's simple but powerful. Q equals M times Cp times delta T here. Q is the cooling load, basically, how much heat we're removing. The M stands for the mass flow rate of water. Cp is the specific heat capacity of water, and delta T is the temperature difference between the water entering and leaving. By knowing the flow and how much the temperature changes, we can calculate the actual cooling power in kilowatts. This formula is fundamental in chiller system design. Let's break down a key formula for chilled water systems, the simplified HVAC equation. It calculates cooling capacity in kilowatts. We multiply the specific heat constant of water, which is 4.187, by the flow rate in liters per second, and then by the temperature difference in degrees Celsius. This formula helps us understand how much cooling power a system delivers, based on how much water flows through and how much it cools down. It's a straightforward way to connect flow, temperature change, and cooling output. Let's walk through how we calculate cooling capacity in a practical example. First, we find the temperature difference. That's the entering water temperature minus the leaving water temperature. Here, it's 12 degrees minus 6, giving us a delta T of 6 degrees Celsius. Next, we use that difference along with the chilled water flow rate and a constant to find the cooling capacity. Multiplying these values, we get a cooling capacity of 2,135 kilowatts. This step is essential for understanding how much heat the chiller can remove. Now, let's look at how we calculate the actual coefficient of performance, or COP, from real site data. Here, the COP is 5.47, which we get by dividing the useful output, 2,135 kilowatts, by the measured power consumption, 390 kilowatts. This simple ratio gives us a clear picture of system efficiency in the field, not just on paper. Understanding this helps us see how well the system performs under real-world conditions. Let's talk about why the coefficient of performance, or COP, isn't a fixed number. It actually varies all the time, going up and down as conditions shift. Things like ambient temperature, refrigerant condition, fouling inside heat exchangers, and compressor loading all play a role. Cooling tower performance and chilled water temperature matter too. Even the condenser temperature and load variation affect it. Many new engineers assume COP stays constant, but that's not true. Understanding these factors helps us see why COP changes during operation. Let's talk about the optimal operating zone for chillers, which usually falls between 40 and 70% load. Efficiency, measured by the coefficient of performance, or COP, varies depending on how hard the chiller is working. Most buildings don't run their chillers at full capacity all the time. Instead, they operate mostly within this mid-range load. Understanding this helps us design systems that perform best where they spend most of their time, rather than just at peak capacity. It's all about matching efficiency to real-world conditions. Modern chillers are built to be smart about how they use energy. When cooling demand drops, the system doesn't just keep running full throttle. Instead, the compressor unloads, which means it slows down or cycles less. This reduces power consumption significantly. At full load, the chiller runs near its maximum capacity, with the compressor working close to its rated condition. But at part load, it adjusts, saving energy while still keeping things cool. This balance is key to efficiency. Let's talk about a common issue with older chillers. They're inefficient when running at part load. These chillers keep the compressor spinning at a fixed, constant speed, no matter how much cooling is actually needed. That means they use more power than necessary during low demand periods. The compressor never slows down, so energy consumption stays high even when it shouldn't. This fixed speed operation leads to poor part load efficiency, making these chillers costly to run and less environmentally friendly. Let's talk about efficiency and how modern chillers keep things running smoothly. These systems use variable speed drives, or VSDs, sometimes called variable frequency drives, VFDs. What they do is adjust compressor speed based on the actual cooling demand. That means less mechanical stress, smoother operation, and a lower starting current. Plus, they improve the coefficient of performance when running at part load, which cuts down electrical consumption. In short, they make chillers smarter and more efficient. Let's talk about why variable frequency drives, or VFDs, improve efficiency so dramatically. The key is the cube law. Compressor power changes roughly with the cube of its speed. That means even a small drop in speed leads to a big drop in power use. When the compressor motor runs slower during low demand, it uses far less energy. So, by reducing electrical demand, compressor work, and motor RPM, VFDs save a lot of power without sacrificing performance. Let's talk about kW per ton of refrigeration, or kWTR for short. This number tells us how much electrical power is used to produce 1 ton of cooling. The lower the kWTR, the better the efficiency. In other words, less energy is needed to achieve the same cooling effect. It's a key metric for comparing systems and understanding their performance. We'll explore this unit more, so we really get what it means for efficiency. Let's talk about the relationship between two key measures of cooling efficiency, kW per ton of refrigeration and the coefficient of performance, or COP. They're inversely proportional. As one goes down, the other goes up. In simple terms, a higher COP means the system uses less power per unit of cooling, so the kW per ton drops. Both metrics tell us how efficiently a system runs, just from different angles. Understanding this helps us optimize energy use in cooling systems. Let's look at an example of calculating kW per ton of refrigeration, or kW per TR. Here, we have a water-cooled centrifugal chiller with a cooling capacity of 500 tons. It's using 320 kilowatts of power. When we divide power input by cooling capacity, we get 0.64 kW per ton. This value is considered a good efficiency for this type of chiller, a useful benchmark to keep in mind. Let's talk about efficiency, how well a chiller uses energy to do its job. We measure this in kilowatts per ton of refrigeration, or kW per TR. Lower numbers mean better efficiency. A high-efficiency chiller runs between 0.45 and 0.55 kW per TR. Good efficiency sits just above that, up to 0.75. Average chillers hover around 0.8 to 1, and anything above 1.1 is considered poor. Understanding these numbers helps us choose and maintain equipment that saves energy and cuts costs. Let's talk about how condenser water temperature impacts efficiency. When the temperature is lower, the compressor doesn't have to work as hard. That means a better coefficient of performance, or COP, and less energy use overall. But when the condenser temperature rises, the compressor faces a higher pressure ratio. It works harder, consumes more power, and the COP drops. So, managing condenser water temperature is key to keeping systems efficient and energy-friendly. Let's talk about the cooling tower, a crucial part of the system that often gets overlooked. Even a slight rise in condenser water temperature can cause power consumption to spike. Why? Because the chiller has to work harder. Common issues like incorrect water flow, scaling, fan failure, low airflow, and dirty fill media all reduce cooling tower performance. When the tower struggles, the chiller's efficiency takes a hit. So, keeping the cooling tower in good shape is key to saving energy and maintaining system balance. Let's talk about chilled water delta T, the temperature difference between return water and supply water. In this example, the supply is 6 degrees Celsius, and the return is 12 degrees, giving us a delta T of 6 degrees. A low delta T like this signals poor cooling performance. It means the system isn't running efficiently, and the pumps are working harder than they should. Understanding this helps us spot problems and improve overall system efficiency. Let's talk about what can drag down a system's efficiency, its coefficient of performance, or COP. There are plenty of reasons why it might be low. For example, increased pressure inside the refrigerant system, or incorrect operation and sensor calibration errors. Problems like fouled evaporators, low chilled water flow, or high condenser pressure can also play a role. Issues with the cooling tower, excess refrigerant, or refrigerant leaks all reduce cooling power. And dirty condenser tubes. They push the compressor to work harder, driving efficiency even lower. When it comes to keeping a compressor running safely and efficiently, there are several key parameters we need to monitor regularly. Oil pressure and refrigerant pressure tell us about the system's health. Electrical conditions like voltage and compressor current reveal how power is being used. Then, there's heat rejection, which we track through condenser water temperature. Finally, building load and chilled water temperatures help us understand cooling performance. For a new HVAC engineer, keeping an eye on these site monitoring parameters is essential to prevent issues and maintain smooth operation. Regular maintenance is the secret to keeping equipment running efficiently. When we stay on top of tasks like filter replacement, sensor calibration, and cooling tower cleaning, we boost the coefficient of performance, or COP. That means less energy wasted and lower energy bills. Add in water treatment, oil analysis, refrigerant checking, and tube cleaning, and we're not just saving money. We're also extending the life of our equipment, preventing costly breakdowns before they happen. It's all about being proactive, not reactive. Let's look at some key energy-saving tips for chillers. First, keeping the condenser water temperature low helps boost efficiency. Cooler water means the system works less hard. Next, using a variable frequency drive, or VFD, cuts down power use when the load is light. Cleaning heat exchanger tubes is crucial too. It improves heat transfer, so the chiller runs smoother. And finally, maintaining proper water flow keeps both the evaporator and condenser performing at their best. These steps add up to big savings. Let's keep our chillers running efficiently by avoiding inefficient loading. That means operating multiple chillers properly to improve heat rejection. It also means maintaining the cooling tower so it works at its best. And don't forget to set the correct chilled water temperature. Overcooling wastes energy. These steps help us save energy and keep the system balanced. It's all about smart operation and careful control. Let's clear up a common confusion between two key terms, capacity and efficiency. Capacity is simply how much cooling a chiller produces, the raw output. Efficiency, on the other hand, measures how much power it takes to create that cooling. A chiller might run at full capacity, but if it's using too much power, it's not efficient. Many new engineers mix these up, but understanding the difference is crucial for optimizing performance. Let's compare two chillers that deliver the same cooling capacity, 1800 kilowatts each. Chiller A uses 300 kilowatts of power, while Chiller B consumes 420 kilowatts. That means Chiller A is more efficient, with a coefficient of performance, or COP, of 6. Chiller B's COP is only 4.28, so even though both chillers cool equally well, Chiller A does it with much less electricity. This practical example shows why efficiency matters in real-world systems. Let's clear up a key point about how these systems work. Unlike regular electric heaters, which have an efficiency at or below 1, the coefficient of performance, or COP, is actually greater than 1. That's because the compressor uses electricity not to create heat, but to move it. It pulls heat from the building's water and releases it to the atmosphere. So, a chiller doesn't generate cooling energy, it simply transfers heat from one place to another. This is an important concept for new engineers to grasp. Let's wrap up with a key concept, the coefficient of performance, or COP. It's a simple ratio of cooling capacity to power input. A higher COP means better efficiency, lower electricity costs, and improved system performance. On the flip side, a lower COP signals higher energy use, potential maintenance problems, and poor operating conditions. Understanding COP is crucial because chillers are some of the biggest energy consumers in any building. Keeping an eye on this helps us design smarter, more sustainable HVAC systems. Let's talk about what really drives chiller efficiency. For HVAC engineers, understanding how to calculate this efficiency is key. Modern variable frequency drive chillers adjust compressor speed to match cooling demand, which boosts part load performance compared to constant speed models. But efficiency isn't just about the compressor, it's influenced by many factors. Maintenance condition, cooling tower performance, compressor type, chilled water temperature difference, condenser water temperature, and load conditions all play a role. Keeping an eye on these helps reduce operating costs and optimize performance. Today, we're wrapping up with a focus on chiller efficiency, a key part of engineering excellence, HVAC performance, and energy optimization. By keeping a close eye on operating parameters and staying on top of maintenance, a chiller can run smoothly for years. This means lower electricity bills and steady, reliable cooling. It's a simple idea, but one that makes a huge difference in real-world performance and sustainability. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more